All right. Good evening, everyone present here. Welcome to the PMRF NPTEL session on signals and systems. I am Shouharda Ghosh, a second year PhD PhD student in the Department of Electrical Engineering at IIT Gandhinagar. This is your Monday session for the PMA Signals and System course, and we are in week 4. I hope that these sessions are helping you solve the problems of the assignments, as well as in case you are taking the course in your semester, then I'm sure this must be helping you in solving your assignments as well as the problem sheets, and also getting a good understanding of the concepts and the intricacies involved in analyzing signals and systems. Okay, so we are in week 4, and in this week we have delved much more into Fourier transform and some of its properties. So we will like some of the properties that we had learned previously was the linearity, which stated that if you have two signals x1 and x2 and you combine them linearly using coefficients a and b, alpha and beta, then the corresponding Fourier transform is also the linear combination alpha x1 omega plus beta x2 omega. Then you have the time shifting property, where if you have a signal xt delayed by tau units of time, then its corresponding Fourier transform as a complex exponential term corresponding to tau delay introduced along with the original Fourier transform. And we had also derived these properties in our previous week. Then we had something called the modulation or frequency shifting. So the rudimentary version was that if we multiply the signal with a complex exponential at a fixed frequency cap omega naught like this, then its corresponding Fourier transform has the spectrum x of omega shifted to omega naught. So for example, if you have some kind of a signal x of omega which looks like this, now after multiplying it by e to the power j omega naught t, then the spectrum shifts towards omega naught as the center. Is somebody trying to ask something? No, fine. Then we have a more realistic, since complex exponentials actually cannot be are not something physical or realizable in a direct sense. I mean, you cannot use signal generators to generate complex exponentials. Then we define the something which is realizable, wherein you take the signal x of t and you multiply it by a sinusoid or a cosine, which I am denoting by this symbol. This symbol, which you will encounter very much if you are into communication systems or if you are designing circuits for communication system, then this actually denotes an oscillator. Oscillator is a electronic device that generates frequency, that generates a sinusoid of a fixed frequency. And when we have these multiplication of xt with the sinusoid of a fixed frequency, this is called the modulated output. And the corresponding Fourier transform is given by 1 by is given by pi x of omega minus omega naught plus x of omega plus omega naught. So if you look at the corresponding spectrum, if I consider this triangular spectrum and I look at the modulated version, so you look at this is how the spectrum will look like. And in a sense this is more realistic, because let me give this as a homework for you, that for real signals mod of x omega equals modulus of x of minus omega. Try to prove this. It's very simple. What this means is that the magnitude spectrum, the Fourier transform x of omega, if you take its magnitude, then it is symmetric around 0. It is symmetric around the vertical axis. So the hint to solve this is to consider the definition of a real number. The definition of real number is the number is equal to its conjugate. In other words, the imaginary part of the number is 0. Okay, very simple. Fine. So we have learned about the modulation thing. Okay, now we will get down into some problem solving of previous year's assignments, and through these I may introduce some of the concepts which were introduced in this week's lectures. Okay, so let's look into question number 1. So we are given we are given a signal that starts from -1, something like this, then something like this. Okay, minus 0.5, and then you have 0.5 and 1. Okay, so if you are watching the recorded version of this, then you may pause the video for a while and try to find its Fourier transform x of omega. Alright, so although it may look a bit if you are solving this for the first time, it may look a bit tedious, but in reality it's very simple, and in fact there are multiple ways of solving it, and I'll show you a few of them. Okay, so let me solve it using the first approach. So approach number 1. So what can be approach number 1? Let me draw the signal once again. -1, minus 0.5, 0.5 and 1. Alright, and this is a height 0.5 and this has a height 0.5. Both of them have height 0.5. Okay, so now I can write this signal as the sum of two signals, or in fact there are two ways of decomposing it. You can write it as a sum of signal, a rectangular function that starts from -1 and ends at -1 and has a height 5, and you have another signal that starts from -1 and ends at -0.5 with a height 0.5, and another signal that starts at 0.5, ends at 1 and has a height 0.5. That can be one kind of decomposition. Another decomposition that can be done is start with -1, end at -0.5, it has a height of 1, then and rest of it. Whenever I am drawing such sequences or such diagrams, it means that if I am not considering anything else, it means that for this or this or this or any other signal, the rest of the part is 0 whenever anything is not being shown. Alright, so you have the central portion that starts from -0.5, ends at 0.5, has a height of 0.5, and the final piece similar to the first piece, height of 1, starts at 0.5 and ends at 1. Okay, in all of these cases, in all the three cases, the most common part is that it's a rectangular piece. It's a rectangular function, but either the amplitude is scaled up or the width is scaled and or the position is shifted. Okay, very important point. So now let us go back to our previous notes and see what was the function for the transform of the rectangular function. So the rectangular functions this Fourier transform is something that you should always keep in mind. You should never it should be in your tips. In fact, if you are preparing for GATE, you should in an instant you should be able to tell the Fourier transform. So if it's rect of t upon capital T, its spectrum is sinc omega t. Okay, fine. So let's rewrite that over here. We have minus t upon 2 to t upon 2, which means if we have a rectangular pulse with amplitude 1 and with a pulse width t, if we have a rectangular pulse with a pulse width capital T, amplitude 1 and centered at 0, okay, note this is centered at 0. So in such a scenario, its Fourier transform will be t sinc omega t upon t. Alright, so in this case I am taking the definition of sinc as sine x upon x. Alright, fine. Now let us look at the first kind of decomposition. The first kind of decomposition, what do we have? We have this big rectangle starts at -1, ends at 1. So what is the width? The width is t equal to 2. Alright, amplitude is 0.5. So what will be its Fourier transform? Sinc omega 2 upon 2 times 0.5. Let us note each term. T equal to 2 is the width of the pulse. I am using this over here. The amplitude of the pulse 0.5 reflects directly over here. That's it. And one more thing that I forgot to add is the other t. It should be here. Okay, so t sinc omega t upon 2 times 0.5. And what does that give me? that gives me sinc omega. That's our first term. Now look at the other two terms, -1 to -0.5 and 0.5 to 1. Let me call this x1 of t, let me call it x2 of t, let me call it x3 of t. Okay, I will re-emphasize the concepts in such a manner that you will see that in every possible way you will be able to reach this answer in whatever steps possible. In other words, let me reiterate. You can use any formula you want, you can use any symmetry you are able to see the picture, but ultimately you will reach the correct answer. And in this fashion I will also try to revise as many formulae, as many properties as possible through a few examples itself. So if you look at x2 of t, what is the width? The width is 0.5, right? So t is 0.5, the amplitude is also 0.5, a is also, admit a is also 0.5. Okay, so initially if I consider, okay, one more thing, where is this located around? This shift delta t, so actually you have a pulse which was located 0, which was centered around 0, and now it's centered somewhere else. What is it centered around? It is centered around the midpoint of the two edges. And what is that? 0.75. So it's 0.75. So what would be the original spectrum looking like? A into t sinc of omega times 0.5 upon 2. All right. Okay, so and then you have a e to the power, that it is a shifting to the left side, so we will have a positive e to the power j omega 0.75. so we have 0.25 e to the power j omega 0.75 sinc 0.25 omega. All right, and now let's look at this x2. In this case you have the same properties, the width t is equal to 0.5, the amplitude a is also equal to 0.5, and the shift delta t, that's 0.5 plus 1 upon 2, 0.75. so the spectrum turns out to be e to the power j omega minus t times 0.5 times 0.5 sinc of omega 0.5 upon 2, 0.25 e to the power minus j omega 0.75 sinc 0.25 omega. Another way in which you could have solved this without having scratched your head was x3 of t is x2 of minus t. Look at this very carefully. What was my x2 of t? x2 of t looked something like this. And what does x3 of t looks like? Okay, yeah, so x3 of t starts at 0.5 and 1. So as you can see, these are mirror image of each other. And what property will we use? We will use x3 of omega is x2 of minus omega. And what is the main property behind this? The main property behind this is x of at as a Fourier transform of 1 upon mod a x of omega upon a, which was our time frequency uncertainty, which meant that if our time is restricted, then the bandwidth increases. Time and bandwidth are in opposite relation. You increase the bandwidth, the time decreases. You decrease the bandwidth, the time flow increases. Okay, it's like an uncertainty principle. Now let's add all these terms. Sinc omega plus e to the power j 0.75 omega, sinc omega upon 4 plus e to the power minus j 0.75 sinc omega upon 4, and then sinc omega plus, what do you have? I combine this because this is constant, sinc of 0.25 omega e to the power j 0.75 omega plus e to the power j minus 0.75 omega, sinc omega plus sinc 0.25 omega. Note that the definition of sinc that I am using here is sin x upon x. 2 cos of 0.75 omega. Alright, now let me expand it further. Sinc omega is sin omega upon omega, sinc 0.25 omega sin 0.25 omega upon 2 by, okay, so there should have been a t term. Oh yeah, there was a t term which I missed, so it will be 0.25. This will also be 0.25 a omega times 2 cos of 0.75 omega, cancel them, sin omega upon omega plus 2 sin 0.25 omega cos 0.75 omega upon omega. Now, doesn't this look familiar to you? What should we be using over here? 2 sin a cos b is sin a plus b plus sin a minus b. Alright, so what do you have over here? Sin omega upon omega plus 2 sin a cos b, which means sin of 0.25 plus 7.5 that gives me omega, and 0.25 omega minus 0.75 omega minus 0.5 omega. Sin omega minus sin 0.5 omega, because this was a negative argument and I took that out of my sign. Simple. When I finally simplify it all, I get 1 upon omega is 2 sin omega minus sin 0.5 omega. Okay, so this is my answer. I could have also stopped over here. This was also a possible answer, but since you will be having MCQ exams, it's necessary that you look at the form of the options and then proceed. And because the previous year's assignment had this form, I moved further from this step that I'm showing over here. I did further calculations and I reached this step, which is actually the correct answer. Alright, that was one approach of solving. Okay, that was approach 1, and I'm sure that if you take number 2 also, it will be very simple for you, and you will get the same answer over here. Here it will be 0.5, here capital T will be 1, here will be 0.5, simple. I mean, let me brief it out once again for you. You have a rectangle, height 1, starts at -1, ends at -0.5, so it has a width of t equal to 0.5. It is centered around -7.75, and it has an amplitude of 1. So our AT sinc omega t upon 2 becomes 0.5 sinc 0.25 omega e to the power j 0.75 omega. This was the first one. The other one automatically turns out to be 0.5 sinc omega 0.25 omega e to the power j 0.75 omega. And then the other one was this -0.5 2.5. This is centered around 0. This was a into, what is the t? The time difference is 1, and sinc omega upon 2 0.5 sinc 0.5 omega. Okay, so in this scenario you would also require some more calculations. Yeah, let me try to solve this. Sinc 0.5 omega and 0.5 sinc e to the power minus j 0.75 omega. So what was happening in this case? In this case we had a wider one, y omega plus .5. Okay, so the 2 will come out and cancel with the 0.5, and we will get sinc of 0.25 omega cos of 0.75 omega. Alright, so now what does it become? 0.5 sine 0.5 omega by 0.5 omega. There will be, okay, so the 2 got cancelled over here. Now I break this down further. Sine 0.25 omega cos 0.75 omega, and what is the denominator? 0.25 omega. Omega upon omega. So multiplying the denominator and numerator by 2, we have 0.5 omega, and here sine a plus b plus sine a minus b, and what do you get over here? Sine 0.5 omega upon omega plus the 0.5 comes over 2 sine omega upon omega minus 2 sine 0.5 omega upon omega. So you are almost there. Like this, subtraction takes place, and finally we reach our answer. Is the same process but it viewed in a slightly different manner, and you get the correct answer. So it means that even if you see in the intermediate step, you may think that this answer and this, both of them are quite different. Okay, both of them are, they look significantly different, but they're actually entirely the same. So often you should, what you should try to do is that you should always simplify the options, or try to modify the options to a simpler form and simplify your answer to a form, so that you can match them turn by turn. Okay, this is the first approach, where you actually break down the single rectangular signal into sub signals. Okay, this is approach 1. Now let me show you the approach 2. So in approach 2, just hold on a second. Okay, so in approach 2, let us first draw the signal once again. Point 5, 1, 0.5 and 1. Alright, so let me try to write this signal in terms of the unit step function. So what is a unit step function? The unit step function ut is 0 over here and 1 over here. Okay, 0 and 1. So now how will I write this in terms of unit step function? Okay, so few preliminaries. If my signal ut shift starts from a different point, let's say 5, it becomes ut minus 5, and it keeps going on forever. Now if I want to make a pulse, okay, I want to make a pulse that starts at 3, okay, starts at 3 and ends at 5. How will I make it using unit step? So you have one unit step that starts at 3 and goes like this. That's u of t minus 3, and then we have to stop it at 5. So that means we have to add or subtract another unit step, which, let me say I add another unit step which is negative sign and starts at 5. Okay, so this is 1, this is minus 1. I add the 2 and see, from 3 to 5 the addition gives me a 1, and anything outside that gives me a 0. So I add them and I get this. Okay, so this is actually u of t minus 3 minus u of t minus 5. This is a very useful way of representing signals. So you can also interpret as having 0 over here, and the first unit has a jump of 1. so I only multiplied by u, right, u of t minus 3. Then I continue going, and the next jump is encountered at 5. So based on the next jump, I see there is a change in height from 1 to 0. So what do you see? There's a delta of minus 1. So then I write minus u of t minus 5. Let me give us some random example that will help illustrate this process in a much more interesting and interactive manner. Let me say this is 2, this is 5, this is 7, this is 1, this is 3, this is 4, this is 0, minus 1. This is somewhere. So how will I start? Go extremely left towards minus infinity and start moving from minus infinity. Go on. Stop at the first discontinuity. I stop at the first discontinuity and I see, okay, I one thing I forgot. I should have mentioned the timestamps as well. This takes place at minus 5. This takes place at minus 3. This takes place at minus 1. This takes place at 2. This takes place at 5. This takes place at 7. Start moving from extreme minus infinity. Encountered the first discontinuity. Encountered where? Encountered at minus 5. Encountered at minus 5. And what is the change? I start from 2 and go up to 5. Okay. Yeah. So before all of it, it was only 2. Okay. It was only 2. We would rarely be encountering this, so let me write it 0 for the sake of completeness. So we start from 0 and we encounter a jump. And what is the height of this jump? The height of this jump is 0, 5 minus 0, that's 5. The minus 5 is my, let me write t naught for the time when I encounter this discontinuity, and delta for the jump amplitude. Jump amplitude is 5. So what will I write? 5 u of t minus 5. Okay, so the first jump is of 5, starts at minus 5. Now I continue going. Again I encounter a discontinuity. Jump is at minus 3. What is the magnitude of this jump? 7 minus 5, that's 2. So I will add 2 unit step t minus of minus 3. I continue, encounter another discontinuity, but this is a fall. This is a fall. What is the magnitude of this fall? 1 minus 7, sorry, what is the height of this fall? 1 minus 7 minus 6. Keep the sign in mind, okay? So minus 6 u t minus of minus 1. I continue going, again another jump at 2. From 1 I jump to 3. That gives me a height of 2. So again plus 2 u t minus 2. I continue, again another jump at 5. From 3 to 4, height is 1. Alright. Height is 5. Height is 1. So it will be u t minus 5. Then I continue. I go down. I see from 4 I fall off to minus 1. That's a fall of how much? -1, -4, -5. At 7, right, -5, I continue. So it will be -5 u t -7. So the overall signal turns out to be 5 u t plus 5 plus 2 u t plus 3 minus 6 u t minus t plus 1 plus 2 u t minus 2 plus u t minus 5 minus 5 u t minus 7. All right, so we have represented the signal using summation of unit steps. Only by using unit steps we have represented this entire signal. All right, and let's say the signal started with some other value, let's say rather than 2 0, if it was 2, what would you do? Start from 2 and do all these calculations, calculate all the deltas and then continue, and at the end you add these two. So it will not be 5 over here, it would be 3. Then all those things would have remained same because the other deltas are same. But let's say if it started with 2, you should start from here at the point where you have the first discontinuity. So you have 2, then 5, then your delta becomes 3. So you would have 3 times u of t plus 5, and then you would have continued the way I have shown you using all these delta values. And finally, after all these u terms, you finally add a simple plus 2, where that means you have shifted up the signal by 2. Or other thing that I would, okay, all right, so this is how we have represented the signal in terms of unit step. And now let us represent this. It's much easier now, I'm sure. Minus 0.5, 0.5, 1. We start from here. We encounter our first jump from -1. It goes from 0 and terminates at 1. So we have u of t plus 1 corresponding to -1 over here. We go on. We stop over at -0.5. We jump from 1 to 0.5. So that's a negative fall. So here is a +1 of change, here is a -0.5 change. So -0.5 u of t plus 0.5. Continue going, you come over here, you have 0.5, you have a jump of positive 0.5. So 0.5 u of t minus 0.5. Start over here, there's a jump again from 1 to 0, that's -1, and you stay there forever. That's minus u of t minus 1. Alright, so this is our signal in terms of u of t. Now let's do something interesting. We know, or if you have noticed very carefully, the unit step function looks like this, u of t. What is the derivative of unit step? It's the Dirac delta function. And note that for a unit step, for one rise, the area for this is 1. Okay, so d dt of u of t is delta t. This is something very important that you should remember. So now we have the signal xt. What will be its derivative? dxt upon dt. Its derivative would be u of t plus 1 will become delta t plus 1 minus 0.5 delta t plus 0.5, because t is not being scaled, it's just shifted. So you have a shifted unit step, so the delta will also be shifted. And I will give you an intuitive look at this. 0.5 delta t minus 0.5 minus delta t minus 1. Alright, so delta, if you look at it very carefully, shows sudden changes. You see, if you look at this unit step, it's all going staying at 0, and suddenly there is a jump. Okay, there is a sudden jump over here, and then it remains constant. The location of this jump is indicated by the position of this delta t. Okay, what am I saying? The location of the discontinuity is shown by the position of this delta t, and the magnitude of this jump is shown by the area or the amplitude of delta t. I would not say amplitude, I would say the area, because had it been 2, then it would have been 2 delta t. The magnitude of delta t is infinity, but the area of delta t is 1. So 2 delta t would have an area of 2. So now let's look at this. It's at minus 1, there's a huge impulse, so there's a change. That's why even impulse at minus 1. You have a change at minus 0.5, corresponding to that there's a impulse at 0.5. There's another change at 0.5, so you have a corresponding impulse at 0.5. You have another impulse at 1, so the corresponding impulse comes over here. Okay, very simple. So how would this look like? You would end up drawing something like this: minus 1, minus 0.5, 0.5, and minus delta. Okay, so can you find, let's say this signal is yt. Will it be possible for you to find the Fourier transform of yt? Very easy. We know that the Fourier transform of delta t was 1. We learned it the previous week. So the direct delta of delta t minus tau would be how much? E to the power minus j omega t. As simple as it could be. So if I look at yt term by term, I can easily find the Fourier transform. So what can I write about y of omega? Y of omega is e to the power j omega minus half e to the power j omega upon 2 plus half e to the power minus j omega upon 2 minus e to the power minus j omega. Alright, so now let's group the terms together. Whenever you see such conjugate or anti-conjugate complex exponentials, always try to group them. What would it be? 2j sine omega should be minus, since there's a half term, j sine omega upon 2. Now how do we obtain the Fourier transform of xt? Let's look at this. We wrote yt equals to dx of t on dt. Alright, see, I am dealing with for the last almost 48 minutes I have been dealing with only first one question only. You might be thinking, why am I doing this? But it's using a single question that I am trying to cover multiple concepts over here. Okay, I am trying to cover multiple concepts using a single question so that all of them may get covered. Okay, using a single example, I have shown you so many properties. I have revised the sync property. I have revised the time reversal property. I have also shown you briefly this scaling thing. Okay, scaling thing could also be applied over here if you have x of sorry, I am extremely sorry. So if you have this t equal to 2 shrinking to t equal to 1, you could have applied shrinking property directly over there. Then yeah, so all these trigonometric things took place, and now this completely different thing, we'll reach the answer soon, but you see multiple concepts are being involved. So now how do you obtain the Fourier transform of this? So now let's look at the definition of inverse Fourier transform. X of t is 1 upon 2 pi integral over minus infinity to infinity x of omega e to the power j omega t d omega. Yt is what? D derivative of x of t. And so what would that mean? I would have to differentiate this entire expression with respect to time t. Alright. So what would that mean? 1 upon 2 pi integral minus infinity to infinity so of omega. All of this is, we are differentiating only the variables of time and keeping the frequency variables constant. So what do we get over here? Minus infinity to infinity. So differentiating e to the power j omega t, j omega comes out. Now let's compare it with the Fourier transform of yt. If I do a term by term mapping, what do I get? I get y of omega is j x of omega. So what do I end up getting? I end up getting that the derivative of xt has a Fourier transform of j omega x of omega. If I repeat this operation n times, you can easily prove by reapplying this, like taking dx of dt as y and finding dy of dt, then you will be able to easily see that you have the nth power of j omega. Alright. So what was our y of omega? Our y of omega was this thing, 2j sine omega minus j sine omega upon 2. Y of omega was 2j sine omega minus sine omega j sine omega upon 2. Now yt was equal to dx of t dt. So what would that mean? Y of omega is j omega x of omega. So what do we have? X of omega is y of omega upon j of omega. Substituting it back, what do we get? We have the cancellation of j's. Okay, then let me show it over here. Two j sine omega minus j sine omega upon 2 by j omega. The j's get cancelled and I finally end up getting 1 upon omega 2 sine omega minus sine omega upon 2. So you see, I have used a completely different approach where I write the signal in terms of unit step and then differentiate it and then directly apply j omega, the differentiation property over here, to reach the answer. But you notice, because I understood the property of the signal, I was able to reach the answer much simpler. So if you have some signals which are which you can write in terms of unit step function, that would be much better compared to this rectangular function thing, because you may often forget the Fourier transform of the rectangular pulse. Although you shouldn't, but I would personally prefer using the second approach. Alright, so we have covered a lot in a single example. Let's go for the second question. The second question over here is something like this: minus 1 1 1. This is minus 1, this is xt, this is t. Again we have been asked to find out the Fourier transform of this signal. Okay, but there is a catch over here. We know the formula for the signals, in the rectangular signals in this thing, Fourier transform, but we don't know this is made up of lines. Okay, these are not straight lines, these are like triangles. Okay, we have triangle signals. Okay, now triangle signals are something that we have not discussed and we have not found its Fourier transform. You may attempt finding it, but then in a short span of time finding the Fourier transform wouldn't be so easy or wouldn't be so helpful. So I would share a very smart approach to solve this. In order to understand this approach, let me talk about a method, a signal representation. So the basic signals that we have learned till now were the unit step unit impulse function, Dirac delta function, and the unit step function ut. So one is a single line, one goes up and stays constant. So now, and we notice the relationship. Delta t is the derivative of the unit step, and unit step is the integral. Okay, unit step is the integral of the impulse. So you integrate one or you differentiate the other, you have such a big, you have this cycle going on. Now let's go one step further. What can we have? The next step that actually comes us to is the ramp function, also called RT. So what is ramp function? The ramp function is defined something like this. The ramp function, just like the previous ones, where 0 for t less than 0 and it's equal to t for t greater than or equal to 0. Alright, so I would like to draw some straight images because I have not been drawing them for a long time. Okay. So RT signal, that should be going up like this, and for the other interval it stays like this. Okay, 0, and to indicate the slope I write something like this, that is 1, the value is 1, the slope is 45 degrees. Alright, so how can I write this ramp? How can I intercorrelate this ramp with the previous signals? So you see, if I draw a function ft equal to t, it would look something like this. Now I multiply this with the unit step function u of t, then I get this function. That means that ramp t is t times ut. Alright, now let's get a bit fast. We draw ramp like this. Now let's suppose that our ramp signal starts from a different point, say from 2. What do we write it as? And the slope remains the same at 1. Okay, so at 3, what should be the value over here? The value over here should be 1, because the difference from the starting point is 1. This is ramp of t minus 2. And now let's say that the slope has increased. How has the slope increased? From 1 to 2. That means if this is 2, this is 3, this value turns out to be 2. So it becomes 2r of t minus 2. Okay. Let's say I see some interesting case where there is a ramp starting and suddenly it becomes flat and it goes down. Let's say it starts at 0, comes to 2, it becomes 3, this is at 4, and this ends at 7. Okay, so how will I write this function as a as something in terms of the ramp signal? So I initially come over, no, I shouldn't use this. I initially come and stay and I see that there's a 0 over here and there's a sudden change. The change takes place at 0 and there is a rise. What is the rise? The rise over here will not be the amplitude change, it will be the slope. In the earlier case of the unit step, we were looking at the changes in amplitude, okay? Changes in amplitude of the vertical lines. Here we will not look at the amplitude change, we will look at the slope change. So initially the slope over here was how much? 0, because it was a flat line. Now what is the slope over here? T is 0. Slope, the change in slope is, it's 3 upon 2. Alright, so what will we write? The slope is 3 upon 2 and the ramp starts at 0, 3 by 2 ramp of t. Now we continue moving. Okay, so I started moving from 0 and I encountered this ramp. Suddenly I see that it has become flat. Where did it become flat? It became flat at 2, and because it became flat, there must have been a change in slope. So why was there a change in slope, or how much was the change in slope? Had there not been change in slope, it would have continued to move like this all along with slope 3 by 2, but here this slope has become 0. So what is this change in slope? 0 minus 3 by 2. So the delta m is minus 3 by 2. So what do we write? Minus 3 by 2 change in slope times ramp at minus 2. I stop over here and I continue. Then I go on and I reach another change point. Where is the change point? 4. What was the slope initially? 0. What is the new slope? The height is 3 and magnitude is 3. Okay, height is 3, change, sorry, it's not a magnitude, is the base. The base is 3 and it's downward direction, so the slope is minus 1. The change in slope turns out to be negative once again, so I'll write minus ramp at t located at 4, start going downwards. I stop at 7 and I see another change. What is the change? Had I been continuing along this, I would have moved down and down, but I see I am at slope 0. So what is the change in slope? Initial slope was minus 1, now the slope is 0. So it's a positive change in slope, so it would be 1. So what do we write? Positive change in slope 1 into ramp of t. Where's the ramp starting from? 7. Okay, so you see I have written this entire trapezium, and that too with not equal slopes. There are different slopes. So this is how my signal x of t looks like. Now An interesting property which I would ask to think about is that this ramp function, if you differentiate this, you would end up getting the unit step function. Constant, and if you integrate unit step function, you get the ramp function. So if I were to add something over here, I would give the ramp function. You can go furthermore, but actually we in most of the exams or the questions we deal up to the ramp function, because beyond it becomes too complicated and the shapes become more or less the same. They start looking same because these are polynomial curves of the power 2, 3, 4. They start looking same. They don't make much of a difference visually. So you have the unit step function is the derivative of the ramp, and the ramp function is the integral of the unit step function. So okay, so that integration is with respect to the variable tau, not t. All right, so now let's say I take its first derivative, dx of t dt. What would it be? First of all, it gives me the slope. So 3 by 2 ut. So at every point, whatever is the slope, that comes out. So if I do differentiation, I get this. Very simple. We don't need to worry about all the internal arguments. Just replace r by t. How will this look like if I ask you to draw this? So 0, I have 3 by 2. At 2, I have 3 by 2 minus. At 4, I have minus 1, and at 7, go down. Okay. So you see, dx upon dt shows me for every point at every point t what is the slope of the signal. Okay. Now let's differentiate this furthermore, because I want to reach this signal in terms of Dirac delta function. Why? I'll show you very soon. 3 by 2 delta t minus 3 by 2 the t minus 2 minus delta t minus 4 plus delta t minus 7. All right. Okay, so now let's try to do this with our signal over here, and this is a bit trickier than what I have shown. Okay, minus 1 1. I start from here and I suddenly encounter a change. What is this change? This change is change in amplitude, not in slope. It's a straight line. So what will I write first? And the change in amplitude is 0 to 1. That's a positive change. And where is it happening? It's happening at minus 1. So I write u of t plus 1. Alright. Now what do I see? I suddenly see a change in slope. And when I see a change in slope, that would mean a ramp function. Alright. So a ramp function goes down. Where does it start? What is the change in slope, or what is the slope over here? The slope is 1 upon 1 and it's negative, so it's a minus r of t plus 1. Alright. Now what do I see? At first it was supposed to go down, but there is a change in slope first. So in order to counter this change in slope, or in order to show this effective change in slope, okay, it was supposed to go down, but I am making it go over here. So we add a change in slope positive 1 r of t minus 1. But notice now I have this constant line going over here because it is not moving downward, it is going the ramp. But what am I seeing? I am also seeing a change in amplitude also. Rather than this, I am saying this is the signal. That means I have gone downwards as well. And how much have I gone down? By plus 1. So what should I write? Plus u of t minus 1. Alright. So how can I write xt? Xt is u of t plus 1 minus u of t plus 1 plus u of t minus 1 minus ramp of t plus 1 plus ramp of t minus 1. Let me group the unit step and ramp separately so that I can easily deal with them. x1t. Let me deal with x1t. x1t is u of t plus 1 plus u of t minus 1. How does it look like? This is just for practice. It starts from minus 1 and at 1 it goes further up. This is how it looks like. Okay, so now if I differentiate this with respect to t, I get two Dirac functions, delta t plus 1 and delta t minus 1. I take their corresponding Fourier transform. J omega x1 omega is e to the power j omega plus e to the power minus j omega. And what is this? 2 cos omega. So x1 omega is 2 cos omega upon j omega. This was our first part. Now let's look at the second part. x2 of t is minus r t plus 1 plus r t minus 1. How can it look like? How will it look like even? At minus 1 I have a negative slope going up, and at positive 1 I have a positive slope which stays down like this. Alright, so here it's 0, here is minus 2, the amplitude. Now if I differentiate it, x2 prime t is minus u of t plus 1 and u of t minus 1. I further differentiate it. x2 double prime of t gives me, then it gives me the Dirac function. I wanted to reach these Dirac functions so that I can find their Fourier transforms very easily. And what do I use? It's a double derivative. I use this rule over here. The nth derivative gives me the Fourier transform of the nth derivative is actually nth power of j omega. Nth power of j omega. So now let me take their corresponding Fourier transforms. J omega whole square x of omega equals minus e to the power j omega plus e to the power minus j omega. So it's minus omega square x of omega equals minus 2j sine of omega. Cancel them. X, this should be x2 actually. x2 of omega is 2 sine of omega square, or okay, minus 2j cos omega upon omega. Now how can I obtain this x of omega? X of omega is x1 of omega plus x2 of omega. x1 of omega was minus 2j cosine omega upon omega. x2 of omega was 2j sine of omega upon omega square. So further simplifying, we take the 2j omegas outside. I have sine omega upon omega minus cosine of omega. Alright, so this is the spectrum of the signal that I have shown over here. Okay, so if you try to do it using manual integration techniques, it would be really tedious for you, because you have to take ax e to the power j omega and further do it down. So rather than doing that, write this signal in terms of ramp function. And actually we noticed over here this signal was mixed in the sense that you had to use both unit step and ramp signal. So whenever you have such mixed signals, first write the signal, then as I have shown over here, segregate the signals, segregate the unit step signals and segregate the ramp signals. Alright, and then take the unit step signals, take their first derivative and then you apply the differentiation property of the Fourier transform. And similarly, x2 of t is in terms of ramp signal, then you differentiate them twice. J omega square will be something that you need to take into account, and you get x2 of omega, and finally you add the 2 and you get the correct answer over here. Alright, okay, so now we go on to question 3. So we are doing very few questions today, but in each question we are covering a lot of concepts. We are supposed to calculate the Fourier transform of e to the power minus 0.5 t sine 3t. Okay, let us see how we can do it. So in all such cases, remember that we don't need to go for the direct process, otherwise it would be too tedious. Let us see this process. So if you remember, we had the signal e to the power minus a mod t, which actually looked something like this. Alright, now if I take its Fourier transform, what was the Fourier transform? If I remember rightly, it was 2a by a square plus omega square, because we had this e to the power minus at and e to the power at for the negative side, so we added their Fourier transforms earlier, individual. Alright, and this is the first concept. And then we also remember that Okay, so let's derive this. We have a signal mt whose Fourier transform is, okay, so let me segregate them. This is one concept and the other concept now, which has a Fourier transform of m of omega. So now what do we write mt sine omega t as? We write it as mt upon 2j e to the power j omega t, let's say it's omega naught, minus e to the power minus j omega naught t. Now we use the complex modulation formula that I had just mentioned in the beginning of the session. So what was that? This one would give me m of omega minus omega naught, and this will give me m of omega plus omega naught. Alright, so now can we look at the pattern? We have e to the minus 0.5 mod t, whose Fourier transform can be written as 2 into 0.5 square omega square, that's 1 upon omega, 1 upon omega square plus 0.25. okay, and then that's our m of omega, and now we are modulating it with sine 3t mt. This was our mt, which would give me Fourier transform 1 upon 2j m omega minus 3 minus m omega plus 3. Let's proceed with simplifying this. 1 by, so whenever you have such term m of omega minus 3, okay, and you are, then what you should do, substitute omega by 3 into this. Omega minus 3 whole square plus 0.25 minus 1 upon omega minus 3 plus 3 whole square plus 0.25 to 1 upon 2j. Now there will be a bit of bad maths. Omega plus 3 whole square, oops, why did I write it twice, plus 0.25 omega plus 3 whole square plus 0.25 minus omega minus 3 whole square minus 0.25. okay, let's cancel the common terms. Omega square plus 6 omega plus 9 minus omega square minus 6 omega plus 9 omega square minus 6 omega plus 9.25 omega square plus 6 omega plus 9.25. Let's cancel the common terms. One upon 2j 12 omega, and here if I notice carefully, it's omega square plus 9.25 minus 6 omega and omega square plus 9.25 plus 6 omega, and I use the a plus b times a minus b equals to a square minus b square, and I get omega square plus 9.25 whole square minus 6 omega square. So our x of omega turns out to be minus 6j omega, I take this j upwards, omega square plus 9.25 omega square minus 36 omega square. Okay. Alright, so you have seen that how using the properties without direct integration we can easily obtain the Fourier transform, isn't it? So we can use another property over here. What is the property that I'm talking about? The property is, if we have a function f of t and whose Fourier transform is f of omega, and I multiply this f of t with e to the minus at, then wait a second, did I even cover it? T infinity f of t okay, so no, we won't be able to use it directly in the Fourier transform case. We will learn this property will not be applicable, the property that I'm thinking about. Okay, so I hope you learned a lot in these sessions, and let me cover one more property and then I will close the class. The property is something like this. So we just mentioned about the derivative of xt leading to j omega x omega. Now we go the other way around. What should be done on xt to give me dx of d omega? That means the derivative of the Fourier transform should be obtained. So how do we go about it? Very simple. X of omega is integral shown over here. Let me call this as yt. Now let me differentiate it with respect to d omega. So I take this differentiator operator directly inside and I get minus jt outside. Minus jt x of t e to the power minus jt dt txt minus jt dt. I multiply both sides by j so that the minus j disappears because j square equals to minus 1. So j dx upon d omega gives me minus infinity to infinity txt to minus j omega t dt. So what do I obtain? I see that Fourier transform of t times xt gives me j times dx of d omega. And now if I do it further, what do I get? T to the power n x of t has a Fourier transform j to the power n dn x of omega d omega to the power n. So there are a lot more problems that use this property In fact, um, okay, so let's recapitulate, or let me look at all the formulas that we have covered so far, because the signals and systems is a course where you will end up using a lot of formulae. So there are a lot of charts available in standard books. So rect was used. Okay, so in this one the only new thing that we used was the d n xt dt to the power n is j omega x omega and t to the power n, so t gives j to the power n, then the derivative. Okay, so I hope you like this session and it was really beneficial for you. So I am closing this session. So thank you everyone for your kind cooperation.